Thanks a lot. It's great to be here. My name is Amin. I will be doing a postdoc in Steffen Staab's group starting from August. I've been doing my PhD in the last 4 or 5 years in SimTech. I will first give you a little overview about my research in my PhD, and then I will talk about the research direction that I would like to do in my postdoc. So because this is a lightning talk, there's not going to be results, but only the direction that I would like to focus during my postdoc. Okay, this is what I already said. In my PhD, I focused on, I've been working on the intersection of simulation science, machine learning, and high-performance computing. So what I have done, basically, I use high-performance computing for more efficient simulations, and then machine learning for building surrogate models, again, to increase the performance of simulations. And in the intersection of machine learning and high-performance computing, I have done bidirectional contributions. I've used machine learning to increase the efficiency of simulations on supercomputers, and I used HPC techniques for more efficient training and inference of neural networks. But today, I'm going to talk about something different, with similar direction. So I would like to ask you to pay attention to this paper from Neil Thompson from MIT's AI lab. Here they analyze deep neural networks, training cost, and try to relate it to their accuracy improvement. I have 2 plots here. The upper plot shows the error percentage versus the year. So this plot is for image detection, image classifications problems, but the lesson can be generalized to other machine learning problems as well. So we see that here, the prediction is that by year 2025, we will be able to get to 5% error. In the lower picture, we have kind of the cost of this error to get. So we see that to get there, we would need computations, flops of order 10 to power of 18, which I can't even, I don't know how to say it in mathematical terms. And that much of computations would emit CO2, which is equal to the CO2 generated by New York City in 1 month. So this is already a huge problem. This is not affordable. The reason is, the theory says, at least according to the paper, that if we want to improve the accuracy by a factor of k, we would need k2 more data and k4 more computations. And this k4 is only in theory, and in practice, it is seen that it is of order k9. So what happens with this huge amount of extra computations, to get to the 5% error, the training cost of a neural network system could be $100 billion, right? So this is not affordable at all, and the consequence is that we already see that people are avoiding to retrain their network. So there are reports that deep AI and DeepMind have avoided retraining their system when they found out they have had an error in their implementation because of the cost. So we either have to kind of adapt a cheaper training, or we would have to stop using machine learning. So already there are many researches to address this issue. People are designing better hardwares. We have seen that we have replaced CPUs with GPUs and FPGAs, and now, for example, we have now TPUs. The problem here is that this sacrifices the generality of computing. Quantum computing seems to be potentially capable of addressing this issue, but it is not ready yet. People are also trying to use smaller networks. But the problem with the small network is that it does not reduce the training cost, but in the deployment phase, it could help. But when you use it, if you have a smaller network, it could cost less. But for training, it doesn't help. Another technique that people use is they prune the network after the training. What they do is that they look at the weights and they just remove those connections that are less important. But as I said, this really doesn't help to reduce the training cost. Meta-learning is another strategy that people use. Basically, it means multi-purpose systems. For example, instead of training a system to detect dog and another system to detect cat, we just train a system to just detect both. This reduces the number of systems to be trained, but the problem is when we expose these systems to new data sets, the accuracy drops. Research is still going on them. Another direction, which looks really promising and interesting, but it is quite new, is combining expert knowledge with machine learning systems. These strategies are more data efficient. According to my previous experience from simulation, for example, combining partial differential equations with neural networks to learn a simulation system, we can train the network by using much less data, and it performs pretty well. We still have performance issues here because they do not generalize to new systems, but the direction looks promising. So this is what I would like to spend my postdoc on. One specific direction that I would like to work on is to combine causal inference and machine learning, and I think there are a lot of potentials to address many issues, including the training cost issue. And I would love to collaborate with many of you, I mean, if there is any potential for this. So thank you. Thank you very much.